Namaskar and hello everyone. I hope you're doing well. So this is the second lecture in the chapter Dual Nature of Radiation and Matter. Okay, so last day we have seen what is photon. We have understood the properties of photon and we have done a couple of numericals. Okay, so numericals based on energy of photons. Okay. Today we'll see photoelectric effect. So before getting into photoelectric effect, you need to know what is a work function. Work function, you denote that with phi naught. Okay, so uh, like you have a metal plate, say. Now this metal plate will have electrons, free electrons. Okay, or just you can say electrons. Now these electrons will be bound to the metal surface by a certain energy, which you call as work function. Basically that energy is phi naught. Okay, now you have incident light falling on this metal plate. Now if this incident light will also have an energy E. Now if this incident light energy is greater than the work function, or the threshold energy you also call it, or the threshold energy of the metal plate, then electrons will start getting ejected. Okay, so this minimum energy, okay, this minimum energy required to remove an electron from a metal surface, all right, is called work function. Now work function phi naught, you denote work function with phi naught. Okay, so phi naught is h nu naught, just like you had E equals to h nu and that you had hc by lambda. So here also you have h nu naught and hc by lambda naught, where your nu naught will be the threshold frequency and lambda naught will be the threshold wavelength. Okay, we'll see what are they. Here nu was the frequency of the incident light and lambda was the wavelength of the incident light. So now we come to, now you see here you have a table you have a table and here some work function values are given. Okay, so you have a cesium, say you have a cesium plate, potassium plate, sodium plate. Now their work function values are this. That means if you want to have photoelectric effect by a cesium plate, then you need to have incident energy which is greater than 2.14 electron volt. Okay, then only electrons will start ejecting. Okay, these values you don't have to remember. This will be provided in the question while doing numericals. So after what work function, you have threshold frequency. Threshold frequency. So threshold frequency is this nu naught. Okay. Now that was in terms of energy. Previously we talked about in terms of energy when we talked about work function. Okay. Now we are talking in terms of frequency. So if the incident light frequency is greater than this threshold frequency, then photoelectric effect will happen. So how do you define this then? It is the minimum, this nu naught is the minimum, okay, minimum frequency required by an incident radiation to cause photoelectric emission. So you can see the definition here. It is the minimum frequency required by an incident radiation, okay, to cause photoelectric effect. So if you have incident radiation whose frequency is lesser than the threshold frequency, then photoelectric emission will not happen. Okay, so I hope that is clear. And finally you have threshold wavelength. Threshold wavelength, you denote this with lambda naught. Now threshold wavelength is the maximum wavelength. Okay, so you need to have incident wavelength which is lesser than this threshold wavelength for photo emission to happen, for electric emission to happen. Now you can see the definition. It is the maximum wavelength required by an incident radiation to cause photoelectric emission. So I hope that is clear. Okay, so we'll just give a summary once again. So what the definition says, it is the maximum wavelength required by an incident radiation to cause photoelectric emission. Now you see in terms of energy when you talk about, or we can write down, for photoelectric emission to happen, if energies are given, then incident light energy should be greater than the work function or the threshold energy of the metal plate. If frequency of the incident light is given, then incident light frequency should be greater than the threshold frequency. If in the question you are given incident light wavelength, then incident light wavelength should be less than this threshold wavelength for photoelectric emission to happen. So this needs to be remembered. Like if either of these condition is given, or you can say if either of these conditions are satisfied, then all the conditions are satisfied. Okay, so that's your threshold wavelength. Now we come to photoelectric effect. What is photoelectric effect? So it is the phenomena, okay, it is the phenomena of emission of electrons from a metal surface when illuminated by a light of appropriate frequency. So you have a metal plate and you project some, you project some light, okay, high energy light or just light whose frequency is nu, okay. Then if electrons starts getting out from the metal surface, you call this is photoelectric effect. Okay, so it is the phenomena of ejection of electrons, okay, or emission of electrons from metal surface. This is the metal surface, okay, by or you can say from metal surface when illuminated. Now you are illuminating this metal surface with the help of incident light whose energy is h nu or whose frequency is nu. Okay, so we discussed the condition for emission to happen. This condition should be satisfied: E greater than phi naught, nu greater than nu naught, or lambda less than lambda naught. I hope these definitions are clear. We'll see the experimental arrangement now. Okay, I'll just copy down this diagram and we'll go through the explanation once, and then I'll just let you read whatever is written there. So you have cathode. Okay, so this is a vacuum chamber. All right, so this is a vacuum chamber. Inside this chamber you have this emitter plate, you have this collector plate. Now collector plate is the anode and emitter plate is the cathode. So cathode is like negatively, they are electron sufficient, right? And anode is like electron deficient. So when it is electron deficient, then it will want electrons to fall on it. So what you're doing is that from the emitter plate you are allowing some light, you are projecting some light of high energy, okay, to fall on the emitter plate, and such that the condition like E greater than phi naught, this should be satisfied. Okay, when this condition is satisfied, then electrons will start going outward. So these electrons will sooner or later they'll fall on the anode, and then you'll measure the current constituted by this electron with the help of an emitter which is placed outside, and you'll have a rheostat and a battery, okay, which will be connected to the circuit with the help of a commutator. Now that is not shown over here. The commutator and all is not shown over here. However, that is not significant. All you need to know is that the polarity of this anode can be changed. Like once you can put it negative potential, you can put it positive potential, okay, and accordingly you can measure the effects, how the negative potential or the positive potential affect the electrons approaching the anode or the collector plate. Okay, so you have two plates here, now you project some light to fall on the emitter plate. Then what happens? Then electrons start coming out. Now you see, if electrons are coming out, right? Now if the anode is given a positive potential, anode is given a positive potential, then what will happen? The electrons will naturally be attracted towards positive potential, right? And that will constitute a current in the external circuit, right? Now this current will keep on increasing. Now if you keep on increasing the anode potential like plus 1 volt, and then the next time you increase it to plus 2 volt, plus 3 volt, what you'll notice that the electron are accelerated. They start moving faster and faster towards the anode plate, and thereby there will be a certain value of this anode potential, like plus 4 volt or say plus 5 volt, okay, at which like all the electrons coming out, they immediately reach coming out from the emitter plate, they immediately reach the collector plate. Okay, so they will constitute a certain value of current. Now when you increase the potential of the anode plate to say plus 6 volt, you don't see any increase in the current measured by the emitter. So what you say is that the current that was obtained at plus 5 volt is the saturation current. Okay, the current that was obtained at plus 5 volt is what do you call as saturation current. Now that is the maximum value of current which can be obtained under that particular intensity of light. Okay. Now what do? You give a negative potential, okay, to the anode, all right, with respect to the cathode. So now you make the anode as negative. Say you apply minus 1 volt. So what will happen? This minus 1 volt, since now this plate becomes negative, they will start repelling the electrons, okay, with a lesser energy, you can say. Now when you keep on increasing this negative potential, minus 2, minus 3 and minus 4, then gradually the repulsion strength will keep on increasing. Now say you have a minus 4 volt negative potential for which no electrons approaching the collector plate, they reach the collector plate. Okay, so under that situation, what you'll say, that this minus 4 volt is V naught. Now V naught, what is the name of V naught? V naught name is like cut off potential. V naught name is cut off potential, or you also call it as stopping potential. Okay, so you also call it as stopping potential. What happens at a stopping potential? Now you'll say, like, when the stopping potential is always a negative value, that you need to remember. So when the collector plate potential is equal to stopping potential, then the current measured at the emitter is 0 straightway. That means no electrons are capable of reaching the collector plate. So under that condition, what happens? Now you see, electrons are moving with a certain kinetic energy, right? So that kinetic energy we can write as half of mv maximum square. Now considering the maximum kinetic energy, now you see there will be many electrons approaching the collector plate. So out of like 10 electrons, there will be one such electron which will have what? Which will have maximum kinetic energy. All will certainly not have the same kinetic energy. So we are considering the maximum kinetic energy only, because if you are capable of stopping the electron moving with maximum kinetic energy, okay, or moving with maximum speed, then you are capable of stopping all the electrons, right? So we need to match the energy of the maximum kinetic energy electron, right? So now this under the condition when I becomes 0 at V equal to V naught, then the maximum kinetic energy of the 4 electron will become equal to the work done on the 4 electron. By whom? By the stopping potential, that is q V naught. What is the formula for work done in relation to potential? There is qv, right? So in this case the potential is V naught. Therefore we are writing down half of mv maximum square equal to W equal to qv naught. Therefore you can write down that. Now since what is the charge here? This q, what is q in our present situation? Q is electron. Therefore we can write down half of mv maximum square equal to ev naught. So this will be a relation to remember. Okay, this is the this relation holds good when no current is measured by the emitter. Okay, or you can also say when no electron reaches the collector plate. All right, so this equation is also known as Hertz equation, and we'll continue the topic in the next lecture. Okay, thank you so much. So this was Photoelectric